Hello and good day everyone, my name is Ron and let's answer some reactor problems. Create a plug flow reactor simulation in DWSim using the following parameters. The compounds are ethylene oxide, water, and ethylene glycol. The property package using Raoult's law, and the inlet stream of the PFR is 1000 kg per hour mass flow, ethylene oxide mole fraction of 0.2, water mole fraction of 0.8 at a temperature of 328.15 Kelvin, pressure at 1 bar, and an isothermal operation. Additional information regarding the PFR is that its dimensions are volume is 1 cubic meter and length is 1.2 meters. Additional information in regards to the reaction rate kinetics is that the reaction rate has this formula K equals Ca and K equals 0.005 per second, and it is a first order reaction as seen here in this reaction rate formula. Now, the questions required is what are the conversion values obtained in DWSim and what is the residence time? Write your answers in the text box provided, submit your DWSim files, so on and so forth. So this is the given, and this is a simple diagram with regards to the PFR, and this is the chemical reaction stated. So we have ethylene oxide mixed with water, and it will yield a reaction of ethylene glycol. So water is a liquid, it's in a liquid state, and ethylene glycol is in a liquid state. However, ethylene oxide is actually in a gaseous state. So let's bear that in mind for a while. And the required, again, is the conversion values of DWSim and residence time. So let's solve this first using DWSim and then calculate it using hand calculations respectively. So we create a new process model in DWSim. Wait for it to load a bit. And then we'll do the general procedure with regards to DWSim. So we'll click next, and then the compounds are ethylene oxide, water, and ethylene glycol. Alright, next, the property packages is Raoult's law, and the system of units will make it custom with regards to what are the given. So we have a mass flow of kilogram per hour, that's good, temperature of Kelvin, and a pressure of 1 bar. We'll put also pressure difference of 1 bar as well, and then that is it. We'll finish, and then we will, before we start, we need to specify our reaction. With regards to my past videos, there were no reactions done there. However, in this problem, there is a reaction that we need to specify and configure. So we go back to settings and go here to reactions, and this is the default reaction. So we'll need to rename this as main reaction. And what is our main reaction? So we need to add here the chemical reactions and click kinetics since we're given kinetic data. We'll name this as production of ethylene glycol. Alright. Then we'll include all in the reaction, and the base component is always the limiting reactant of the reaction. Going back, that this is the main reaction to create ethylene glycol. When there is water, we always assume water or air or oxygen, we always assume them as in excess since they're very abundant in our environment. With that in mind, the logic meaning that the other reactant is the limiting reactant. Since, again, water and air or other components that are abundant in the environment can be treated as excess. So ethylene oxide would be our limiting reactant, which also means it would be our base component. And stoichiometric coefficient. So whenever the reaction, a compound is a reactant, we will put it as negative value. When they are a product, we put it as positive value. So stoichiometric coefficient, ethylene oxide is -1. And why is -1? It's because there's no coefficient here. So we put -1 if there is no number at the side. But if there is a number such as 2, 3, 4, 5, 6, 7, 8, 9, 10, we would treat it as such. But for now, since it's in a reactant and there's no coefficient, we'll put it as 1. Same thing for water, we'll put it here as -1. And for the glycol, since the glycol is a product and it has no coefficient visible, we'll put it as positive 1. Then you will know if your stoichiometry coefficients are good if the stoichiometry is listed as okay. When it means that it is okay, this means that the equation is balanced. So the amount of carbon in the left side is equal to the amount of carbon in the right side. Same thing for hydrogen, and same thing for oxygen. Alright, and then we need to specify our order of reaction. So according to the problem, the rate of reaction for A, where we treat as A as the limiting reactant always, is first order reaction. So we'll put here direct order for the base component is the first order, and we'll put the rest as 0. Next, what is our basis? Our basis is molar concentrations, and our phase is a vapor phase because ethylene oxide is a compound that is in the gas phase. And then we'll put here the minimum temperature and the maximum temperature. So going back, our minimum temperature, our temperature in operating temperature is 328.15. So that means that in order to find a very accurate reaction setting, we need to put our operating temperature, we need to pick our temperature range where the operating temperature is within that range. So if our operating temperature is 328.15 Kelvin, we'll put this as around more so like 200 Kelvin. So vapor phase, simple advance, and we need to specify our rate constants. So our rate constant is K, and K can be equated to A for our Arrhenius equations. So 0.005 per second, and there is no energy constant corresponding to it. So we'll just put it as 0. And then the amount units we'll put here as kilomole per cubic meter for the concentration, and then the rate units is kilomole per cubic meter per second. Alright, and our settings are set. And then, since we have now our reaction specified, we'll now go to the reactors. So we go to the reactor tab, click PFR, and we would have the following streams automatically put together for us. So we'll rename it as follows to ease everything in labeling. So we have the feed, the product, and then the duty. So the feed is in Raoult's law, and the inlet stream or the feed is at 328.15 Kelvin, and then 1 bar, and then 1000 kilogram per hour. Okay, and then for the compound, the mole fraction, so ethylene oxide is 0.2, water is 0.8, and by nature, ethylene glycol is 0 since it doesn't even exist yet, since it has not been reacted yet, or there's no reaction occurring yet since it's still in the feed. Alright? Afterwards, double check your details. Everything looks good. Now we go to the plug flow reactor details. So according to the details here, it operates isothermally, meaning that the temperature in inlet or the temperature of the feed is equal to the temperature at the product. So we'll put here as isothermic, and then we'll specify the reaction. So reaction is the main reaction. We already specified it earlier. And then the dimensions, according to here, the volume is 1 cubic meter, and then the tube length or PFR length is 1.2 meters, and that is it essentially for the details. So the duty, it seems here that the duty energy needs to be given to the PFR. This means that the reaction is endothermic nature since it absorbs heat. Thereby when we touch it using our hands, it feels cold since it absorbs the heat from our hands. But what we need is the conversion values. Values obtained and the residence time. So the conversion value here, according to PFR or the simulator, the conversion of ethylene oxide to the product, ethylene glycol, is 89% conversion, while the residence time is 257.477 seconds. So With that in mind, let us now start with the hand calculation to prove that everything makes sense. So in answering chemical reaction engineering problems, I usually follow a set of steps that will help me assist in the hand calculation. These set of steps are referred to as the CRE algorithm that is inspired by the book of Fogler, The Elements of Chemical Reaction Engineering. And the algorithm are as follows. First, I specify the assumptions that corresponds to the specific reactor in question, which is a PFR. For PFR, it is a continuous steady-state process assumption. It is also well mixed, and the volume changes for each component as it traverses through the PFR. And then after the diagram and assumptions definition, I will do my first step, which is a material balance via CRE algorithm for reactors. So in this step, the first step is the general mole balance with respect to reactant A. So this is the main equation I started with. Then I apply the assumptions I stated earlier. Isolate, using algebra. I isolate that the change in volume is equal to the change in final molar flow rate of A with regard over the reaction rate of A. And in the second step, I define the rate law. Since the rate law is already defined earlier, which is KCA, I have no more need to use the power law model. However, we need to specify that A is negative. The reason why it's negative is because the reason why there's negative sign is because A is being consumed. When it is positive, that means A is being produced. However, if we look at it, this reaction, and we put ethylene oxide as our limiting reactant or a base component, it is actually being consumed as the reaction goes on. Hence why, rather than having positive reaction, there should be a positive reaction rate. It should be a negative reaction rate. That's why I put negative sign next to RA to specify that the A, or ethylene oxide, is being consumed. Next, for the stoichiometry, the third step is defining the stoichiometry in the gas phase. So for the gas phase, it is non-isobaric and isothermal. So for gas phase, so this is the equation regardless if it is gas or liquid phase. For liquid phase, automatic, the pressure difference is negligible since liquids are always assumed to be incompressible. This means that the pressure outlet, the pressure inlet are almost similar. They cannot be compressed, hence this one is essentially equal to 1. However, since we're referring to a gas phase reaction meaning that there is a possibility of compressibility, since the reactant is a gas phase itself, we'll retain the pressure difference ratio. But for the temperature difference ratio, since we already assumed that the operation, or we already set the operation as isothermal, this one is essentially equals to 1. And this one, for liquid phases, this value essentially equates to 0. However, since it is not, we assume that it is not a purely liquid phase reaction since we're mixing gas and liquids, we'll just assume it to be a gas phase since the reactant is in a gas or vapor form. Hence why this value cannot be equal to 0 and we need to calculate this manually. So doing so, the stoichiometric table has the species stat line, which corresponds to the species, ethylene oxide, water, and ethylene glycol. The feed rate to the reactor has the 0 subscript, and then the change in reactor is simply the multiplying the limiting reactant times the conversion value. And negative meaning they are reactant, and positive meaning they are produced or they are a product. And then the effluent rate or the rate of exit is simply the difference between the two. So FAO minus FAOX, FBO minus FBOX, and FCO minus FAOX. So this essentially means that this is the outlet molar flow rate of the specific compound. Then we need to convert this into concentration form. So we'll divide it by the final concentration, which is V. And already know that V has this form. So this is the final concentration form with regards to outlet concentration of A, outlet concentration of B, and outlet concentration of C. And how do we find epsilon? Well, we need to sum all the coefficients in this line. So this is del. We need to find del, and del is the summation of all the coefficients in this line. And epsilon is simply equal to del times the vapor mole fraction of the reactant A. So according earlier that the mole fraction of A or ethylene oxide is stated earlier as 0.2. So we'll put here 0.2, and then we will sum all of the coefficients here, -1 plus -1 plus +1 equals -1, and our epsilon will be -0.2. Afterwards, we we define everything, and then we just simply combine. So how do we combine? We go back to our first step, and we get this derived value from the general mole balance, and then we define it, and we define that we define Fa using this from the stoichiometric table, and then cancel out. We specified that there is no change with regard to the initial molar flow rate, so we'll put this as 0, and hence we're left with this form. And then remember that the reaction rate is being consumed, hence why negative Ra equals Kca, or Ra equals negative Kca. So there's a negative sign here, and that's why this is the final form. And then Ca can be redefined in terms of this equation. So we'll put it as such, and FAO, substitute, and as you can see here, FAO over CAO. And there's another thing you need to know about this, is that F, the molar flow rate, let me add it now. So take note that always the F, or the molar flow rate, is equal to concentration times the volumetric flow rate, regardless if this inlet or outlet. So this means that if this is for the outlet, if F over C is equal to volumetric flow rate, that means the volumetric flow rate at the inlet, that's why there's V0, is equal to these values. So putting these outside, since they are not in, they have no qualm with the integration, since the integration is with respect to x, not these variables, and this is integration with respect to v. Integrating it from 0 to v and 0 to x respectively, we have this equation, substituting everything from the given volume value, and then our given data. The inlet volumetric flow rate, I obtained it from the simulator. And the reason why I obtained it from the simulator is because it is in a feed stream. This is essentially from the given data, and this is calculated automatically using the help of DWSIM. And to ease in calculation, rather than calculating the volumetric flow rate inlet manually, again, I just acquired the value from here. So this is in meters cubed per hour, and I put it here in meters cubed per second. So afterwards, I found out that this conversion using hand calculation would reach 76.53% conversion, and my average residence time is simply equal to the volume of the PFR over the final volumetric flow rate. We defined already the final volumetric flow rate has this form, this one. Substituting it, and since we already know everything, we substitute it simply, and then we have that my residence time, essentially this is actually space-time, and according to other references, space-time is also equated to average residence time. So equating this and that, would have the residence time is 309 seconds. So to finalize, our simulated value is liquid residence time is 257.477 seconds, and the conversion is 89.0209. So equating everything, and let's compare them using a percent difference analysis. So the calculated is 76.53%, and then the simulated is 89.02%. Then the percent difference is around 15.09%. And then for the residence time, 257.477, and my calculated 309.9593, I calculated a percent difference of 18.50%. So it is actually quite large. However, this can be a good estimate since percent-wise it doesn't exceed 20%, 50%. It doesn't even exceed 100%. So the reason for such large differences may be due to the possible gas-liquid mixture phases in the actual reaction. The algorithm that I showed you before, there are only two cases we were taught: the gas phase, purely gas phase reaction, and purely liquid phase reaction. I'm not familiar with the mixture algorithm or the algorithm for mixture phase components, Hence, the reason why I picked gas phase, the gas phase algorithm was because ethylene oxide is in a gas phase itself. Hence, why I picked gas phase case in the algorithm. Also note that the algorithm by Fogler only denotes for case of pure liquid phase reactions and pure gas phase reactions respectively, as I said earlier. Additionally, using this algorithm should traditionally have the rate law followed by the power law model, negative RA equals KCACB. However, a different rate law was given in the problem itself. Normally, when using the algorithm, the rate law should be using the power law model. The power law model essentially states that the rate constant of a reactant is equal to the reaction rate constant K times the final concentration of the reactants, which is the reactants. We have two reactants essentially. We have reactant of ethylene oxide and we have the reactant of water. However, we're already given the reaction rate formula, which is only considering the concentration of ethylene oxide at the outlet. So that's why the power law model was not used here, but the algorithm was equated for the power law model itself. That may be a cause of variation in the calculation. However, the percent difference between the two is actually, it's a good estimate. I cannot say that it is very accurate, but it is a good estimate since we are able to reach a answer almost close to the one given by the simulator. And that's it. Again, thank you all for watching, and I'll talk to you all later.